Hello, everyone. If you're here, please stand by. We'll start in just a minute or two. If you're here and interested in following along, please go to our Jupyter hub now and start your engines. I saw somebody raising their hand, and I kind of wonder what that means, and I'm going to try doing something about that because I'm kind of curious about what that means. Attendees, someone raised their hand. Huh, maybe somebody took their hand down. Okay. So I'll have the Slack channel open in front of me here, and you can ask questions in the Q&A as I go along, and I'll try to stop whenever I see questions show up in the Q&A, depending on whether the timing is good. For those of you joining us now, please get your Jupyter hub started now. Go to hub.neurohackademy.org to join the Jupyter hub, because a lot of this tutorial will use the Jupyter hub. And I'll show you through a little bit of the Jupyter hub before I jump into other things. This seems like a good time since it's probably the first time that you're seeing things in our hub. I should probably get rid of my email here. Okay, so this is our Jupyter hub. This is what it should look like, roughly what it should look like when you log into the Jupyter hub. And the way this works is on the left here, there's sort of like a file navigator. Yeah, just the small server needed. I've been asked. We're not seeing your screen. Oh, okay, I need to share my screen. Yes, thanks, Chris. Okay, now you should be able to see my screen. So yes, when asked what kind of server you need here, just use the smallest server. I don't think we need anything bigger for, in fact, we tested, we don't need anything bigger. And I'm on one of these small servers. This should be fine for this tutorial because we're not going to use very large data. And so as I started mentioning right here, there's like a file folder interface. You can navigate through that to go in and see what's inside of the curriculum. If you click on this folder here, it'll take you back to your home directory. And you can create folders in here. And you can go into this folder, for example, and you can create a new notebook by clicking on this launcher here. So you have different launchers down here of different kinds of interfaces. This starts a Jupyter notebook. If you've never seen a Jupyter notebook before, this is what it looks like. You might change that the name of this thing by right-clicking on the name and type rename, and say my notebook, and start executing code in here. A equals 1. Shift and enter executes this code. And so every cell here is a code cell. I'm writing Python code here. Those of you who are here in this tutorial should be familiar with Python, so this shouldn't be too strange for you. I'm sort of assuming that you've seen Python code before. Many of you have probably seen the Jupyter notebook before as well. And you can write multi-line code here as well and execute that within each cell. So that's the Jupyter Lab interface, the Jupyter notebook. I'll go into curriculum, which is where our curriculum is. This folder here auto-syncs when we make changes to a GitHub repository that contains the notebooks. If you're interested in the GitHub repository, that GitHub repository lives in here. github.com/neurohackademy/nh2020-curriculum contains all the folders for the curriculum, and we sync that automatically into our curriculum folder right here. And so if you click on that and you click through to the folder for MO-high performance Python Rokem, then you'll see all the notebooks that we're going to use during this tutorial. And so the first notebook, and I encourage you to follow along or just watch me as I navigate through this. The first tutorial here is the introduction tutorial, or the introduction notebook. I'm just checking how things are going here. It seems like it's good. So I will start talking first, and then we'll run some code. So the purpose of this tutorial is to introduce you to some tools that we can use in order to speed up Python code. What do I mean by that? So one of the main advantages of Python is that it's really easy to write. It's dynamically typed, so we don't have to worry too much about things like declaring variable types, right? We don't have to say, oh, this variable that I've declared is going to be an integer, always stay an integer. And this other variable here is going to be a floating point number. And in contrast to other languages, it's interpreted rather than compiled. So we don't have to go through a compile loop every time we change the code. Instead, we write code, we run it, and it just runs. And that's because it's an interpreted language, it runs through the interpreter. And while we're running it in this way, we might have code that accepts different inputs that have different types. And so some of this incurs drawbacks in terms of performance, because performance can be rather slow. And that's because when you try to add two numbers to each other, Python might ask something like, are these numbers floating point numbers or are they integers? And it has to ask that every time because addition of floating points is a different operation than addition of integers under the hood. And so when you write number plus number, it needs to ask what type is this variable? And that takes time. And so that has some drawbacks. So it's slow. And the question is, how do we speed it up? And that's sort of what we're going to try to answer in this tutorial. How do we speed Python up? So one thing that we do a lot is using NumPy to speed things up. And that's because if we have data structures that are arrays and all have uniform data type, then we can say something like, we can tell the Python interpreter, look, here's a collection of numbers. They're organized in an array. They have a certain shape, so they have a certain dimensions. And everything in here has the same type. If you're going to add these numbers to these numbers over here or to this number over here, you need to use only one function all the time. You don't need to check every time what type is this number. And so you can speed that up quite a bit. But this kind of vectorization, while very, very effective and in many, many use cases in science, time series analysis, image processing, so on, it works really, really well. Sometimes we can't rely on vectorization, or we want to increase our speed beyond vectorization. And so this tutorial will introduce you to 3 approaches to speeding up Python code. The first approach, delineated up here, is to speed by writing extension code in C. So I'm telling you, well, you write Python because it's dynamically typed and it's interpreted. And here I'm telling you, if you want to speed it up, use a statically typed compiled language like C. But that's very cumbersome. And C is much harder to write than Python. And so the first approach that I'll show you does something very clever. It takes Python code, it compiles the Python code into C code, and then compiles the C code into sort of highly optimized machine code that you can use to run on your data. And the technology that allows us to do that is Cython. That's a library, a Python library that does this. And that's the first approach. The second approach that we'll look at is called Numba. Numba is also an approach that compiles your code to highly optimized machine code, but it takes a distinctly different approach. Instead of translating your Python code to C and then compiling that to machine code, it relies on something called LLVM to compile the code just in time. So when your code runs, it gets compiled. The first time you run a function or some operations, they get compiled to machine code. And then from then on, every time you run that, you get the benefits of the compilation. Finally, the third approach that we'll look at is parallelizing. So you can gain a lot of benefit from parallelizing your Python code. And that's because really, when you run Python code in sort of a single-threaded mode, as we run it usually, you only get sort of a single thread, and that's built into the Python code itself. And we'll look at a library called Bask that does some clever things in order to parallelize your code pretty transparently. So that's the two approaches. But before we dive into each one of these approaches, we need to know whether what we're doing is helping us. And so the first thing we need to do is that we need to profile our code. What is profiling? If we're going to try to improve the performance of our Python code, we want to start by measuring how well the code is performing right now and what improvement can we get through our operations. So at different points in time during the notebooks that pertain to these different ways of speeding up the code, we will measure how long does it take to run some code. And to run that, we will use a magic function. So Jupyter, in addition to being able to run the Python code that you see here, importing NumPy and running some things, is able to run so-called magic operations. So if you see in Python code or in Jupyter code, you see some code that has a % sign before it, that means that that function is a magic function. It's called the magic function. It's not really Python, and this wouldn't work in real sort of Python that you wrote in a py file. But it works in the Jupyter notebook. And so it runs some of the other functions as kind of a magic behind the scenes. So here, what we're doing is we're profiling a simple line of code. Here we're generating matrices, random matrices of increasing size, and we're taking a dot product of these matrices. And each time that we take the dot product, we measure using timeit the time of execution of that code. Let's run that. It takes a little while, and that's because when you run timeit, it runs it several times. So you can see that it ran, what is it, 100,000 times here for the first operation, and then 1,000 times for this operation, and then for the largest size of the matrix, it's running for a while, and it's running probably less times because it adjusts automatically how long it should run. And so you can see that as the size of this matrix increases, the time of execution of this dot product of x transverse a transpose is increases. Okay, so scales up with the size of the matrix. And so the important thing to notice here is we ran timeit on this operation, and it gives us back kind of like a measurement of the time, including even error bars. So that's pretty nice. In addition to the timeit operation on a single cell or a single line, we can run a timeit operation on an entire cell. That's done by putting %% before the timeit magic. So in Jupyter, % sign is a magic that applies to a single line of code, and a % sign is a magic that applies to the entire cell. So here we're doing some slightly more complicated thing. We're taking a random matrix, 100 by 100. We're allocating a distance matrix, and then we're doing this double nested loop to compute the distance matrix between rows and columns pairwise between rows of the matrix. So we're taking row I and row J, taking the difference between I sub k and J sub k, and then multiplying that, eventually summing over the entire row, and taking the square root to get you in every entry the distance between the sort of Euclidean distance between row I and row J. And so running this code here will now time the entire execution. While this is happening, let me take a look at the questions here. Okay. Oh, not really Python. I was asked, what do you mean not really Python? I had a hard time understanding. Oh, this pertains to the magic. The trick here is if I were to put this in a .py file and try to run it through the Python interpreter, the Python interpreter will interpret this as a syntax error. And that's because it doesn't recognize this as Python. But Jupyter does recognize this as Jupyter Python. So it's a little bit of an exception from the syntax of the Python programming language that works in Jupyter. It works in Jupyter and it works in IPython, but it won't work in the regular Python interpreter. I hope that answered that question. I think I'll click answer live and done on that. And hopefully, if you have more questions, you can just type them in the Q&A, and I'll see that. Okay. In the meanwhile, this ran, and we can see that it ran, just once because it took a long time, and it just takes a long time to do this. This is really not the best way to do this kind of operation of calculating pairwise distances between rows of a matrix. But nevertheless, this demonstrates the point. We can profile Python code. Good. Another thing we might want to do that is also very, very useful is to profile code line by line. So when we look at a piece of code like that, a cell of code like that, and we might wonder, well, what is it about this that makes this so slow? Where is the Python interpreter spending most of the time? One way to do that is to write this code again, this time as a function. So you see I defined a function, distance, has no inputs, but it runs the same code that I had in the cell up here, and then run a line profiler on this. So in the Jupyter Hub, we have installed the line profiler package. You can install this also on your own computer or elsewhere using a conda install or even a pip install. Here we're using, again, a Jupyter Magic load-ext, and that means that we're going to have available to us some additional functionality that is an extension of Jupyter through the line profiler package. So I have an extension here, line profiler, and now we're defining a function. And that means that we can run now a magic command. Again, this is a line magic that operates here. LP run, and LP run stands for line profiler run. So the syntax for LP run, for line profiler run, is -f signifies which function is going to be profiled. In this case, we want to profile line by line, profile the execution of the code in this function. And then the next thing here is the function that will be called to execute this. In some cases, the function to be called and the function to be profiled are going to be two different functions. You're going to have some code that you want to profile, and then some other code that calls that code in order to get it profiled. In this case, the code to be profiled and the code to be called are the same. So we're profiling the distance function, -f distance, and we're profiling it by a run of distance parentheses in order to call that. Okay, while running that, let's see the question that came up. Does load-ext work for any package? Is it the same thing as import? Okay, so this pertains to this line here. I'm loading an extension called line profiler, and that's distinctly different from doing import line profiler. Import line profiler would import the library line profiler. Load-ext loads an extension from the library line profiler. For this to work, the authors of the package line profiler need to have written a specific Jupyter extension for this to work. So it's only if the authors have included a Jupyter extension in their library that this Jupyter extension would get, or this IPython extension would get pulled into Jupyter. So in this case, in the line profiler case, and we'll see one more case later on today, there is an extension that gives us this functionality. Otherwise, it wouldn't work. Okay, so let's look at the result of this profiling. So here we get a profiling. It tells us how much this took total to run this function. It took a pretty substantial amount of time, but also it gives us several more pieces of information. It tells us for each line how many times that line was run. That's the number of hits here, the first column. And it tells us how much time was spent on that line. You can see sort of the inner calculation in the inner loop is where most of the time was spent here. And it also tells us the percent of time that was spent here. And this is useful because we can look at the code and we can say, well, most of the time is spent on this line. Let's see if we can optimize this particular line. And this gives us the information that we need in order to improve our code and make it run faster. So this is a more fine-grained way of profiling the code. Okay, let me see what questions people have. This one I've answered, so put it away. Right, why could you have two functions here, function to be profiled and function to be called? The reason for that is that sometimes function to be profiled is called by function to be called through a complicated set of operations. So imagine that function to be called calls several different things, and we're only interested in profiling function to be profiled, the particular function. Then maybe you have a path of execution through here that includes function to be profiled within it, and we're only interested in profiling this function, not this entire function. You can imagine this happening when you have a complicated system that includes many different bits and pieces. You can call it through this function, but you're only interested in optimizing this function over here. So that's why this looks like this. In the case that I've outlined here, things are much simpler. The function that we want to profile and the function that we call are one and the same. Okay. So the next question is, LP run is a function defined in line profile. That's right. When we called this code here, loadx line profiler, that made LP run available to us. So before we ran this, LP run was not available. It's not a generic magic that comes together with the notebooks. It's a magic that becomes available once we run this loadx. The next question is there an equivalent of LP run using .py file types? Yes, the line profiler package includes functionality to run this on .py files. I won't show that here, but you should look up the documentation for line profiler to do that, and we can provide a pointer to that. Right, could you quickly re-explain the function to be profiled versus the function to be called? I think that I answered that. And I'm going to move ahead now for the sake of time. If this still remains a question later on, it's not necessary to know this for what I'm going to show next. If this remains a question later on, we can answer that again later on. So I'm gonna move on. So this is useful because it lets us profile the code line by line and lets us focus on the parts of the code that are performance bottlenecks. I'll just point out here as a complete side note that you can also profile memory performance of code. Sometimes it's useful to not only profile how fast the code goes, but also how much memory each line of the code consumes. And there's another package called Memory Profiler that allows you to do that. And it has a low-dex memory profiler that gives you an MP run that works in the same way that I showed you here, giving you the memory consumption line by line. Okay. One more question here. Could you give an example of how to use LP run in NiPipe workflow? I think that the function to be profiled, function to be called distinction would be useful here, but not sure how. So that's a good question, but it's a little bit hard to do on one leg. I'll give an example using maybe object-oriented code as an example. Imagine that you're initializing an object, a complicated object that contains many different methods here. And there's a method within, one of the methods is the method that you're trying to optimize right now. And in order to access that method, you need to call several other methods as well. Then the function to be called might be one method of your object that then indirectly calls to some other method of your object. And the function to be profiled is that other method of the object. I think I'll defer on that. I understand that this is still a little fuzzy. Let's keep answering that later on in the Slack channel. I'll try to give more concrete examples. For the time being, for the sake of time, so that we have time to look at the other things, I will move on now into some other things. So we've seen how to profile line by line. I actually won't be using the line profiler further in the tutorial later. I'll be using this time it later on. So I think that I'll move on to the next part, and then hopefully things will be clear in the way that I use time it here, and we can come back and talk more about the line profiler at a later stage or on the Slack channel. Okay, so the first approach to speeding up Python code that I told you that I will show you is Cython. Cython is a technology that takes Python code and compiles it into C code, subsequently compiling that C code into highly optimized machine code that you can run. So let's look at a fairly simple example first. Much like the line profiler that I showed before, Cython implements a magic or an extension within the library. So in the case of Cython, we can run loadex Cython, and that would load some additional functionality into our notebook. Before we do that, before we use this additional functionality, let's take an example. Let's define a function in Python. This is a function myPoly that executes a polynomial. So this polynomial takes two inputs, A and B. It multiplies A by this number, 10.5, and adds to it 3 times B squared. That's some mathematical operations executed in Python. And what I'm going to do next is I'm going to define another function called myPolyX. And myPolyX runs the same code, except instead of the inputs A and B, now the inputs are double A and double B. And I've decorated, I've included in this cell, the cell magic Cython. And so when I run that, something happens, this function gets defined, and I'll come back to the differences in just a second, but let's first time the operation of this code. So I'm timing my poly and I'm timing my polyX, and the first one takes 370 nanoseconds to run, and the second one takes 100 nanoseconds to run. So changing the code slightly, including this double A and double B, and running it through this Cython cell magic gave me about a 3-fold speed up in the execution of the code. Okay, so what is the difference? What happened here behind the scenes was that the Cython library took this code, it wrote C code out of it, it read this code, it wrote C code out of it, and it compiled that C code into highly optimized machine code. And so this highly optimized machine code that is running here can run much faster. An important point to note here is that along the way, we told Python the type of the inputs. So we told it that this input should always be treated as a double. It's like a floating point. So we told it what data type we're going to give it. And this one should also be treated as a double. So we told it something about the data types that will be coming in as inputs. And while we could have given it other inputs here and it would have tried to run here, here it will only accept numbers as inputs. So we can only run it with numbers in this case. And so telling it a little bit about the input and then adding this additional compilation stage gives us about a 3-fold speed up. Let's see what questions people have at this point. Okay, this is about profiling, but let's go on to Cython. How much of Cython speedup comes from Cython itself and how much from specifying the data type? That sort of depends a little bit on the particular, on the specifics of the problem that you're running. In this case, I guess we can experiment here by removing the type annotation and rerunning this and seeing what kind of speedup we get here. 370 versus 351. So yeah, a lot of the speed up came from the fact that we told it what types are going to be used. And that's because a lot of the cost of running this code comes from figuring out exactly what these operations should be. And that comes from knowing what the types are. We have to look at the variable, say, is this a double? Is this a float? Is this an integer? And so on. So a lot of the speed up here came from the type annotation. Okay. If you want to run a loop that wasn't in a function, would that work? Would that work if you just put %% Cython in the line above the for loop? That is a good question. If you can just decorate, I haven't seen that done. So I think the way to work with Cython is to define functions and then compile those functions and then use those functions. I haven't seen anyone just kind of decorating a bare code. So we'll stick to that mode here. where we're defining functions and compiling functions. Someone else here is asking when to prefer Cython over Paralyzation or Numba. Maybe we can defer that question to much later when we've seen these other approaches. The gain is amazing. Is the gain similar if we combine it with NumPy functions or functions containing NumPy? Okay, yeah, so you can combine this with NumPy and you can get increasingly faster. You can do a lot of things with Cython to combine it with NumPy. In fact, Cython is written with NumPy in mind, so we can take advantage of the fact that NumPy is parallelized. Let's look at an operation that you couldn't really do with NumPy. Why are the time and number, so first I'll just answer this last question here. Why are the time and number of loops different for the Python versus Cython function? The reason is how long it takes to run. So, you know, in some cases, in this case where it was slow, they're both run at the same time. Jupyter, while it's running this time and magic, it looks and it says, oh, the first time I ran it, it took this long. And when we're timing, we don't want to spend, we don't want to run the same amount of number of loops every time because it might take a long time to time something. If it takes a really long time to run it the first time, we just stop and get back the answer. It's just sort of like an adaptive trick here. Can you do stack heap allocation in Cython? This is a little bit of an advanced question. I'm not 100% sure. I'll just answer a very generic question here, which is the following question. Or really rather, I'd say the following. One of the nice things about Cython is that you can take Python code and you can compile it. And here I've shown you the example where we're compiling something that is rather simple Python code into C. But you can increasingly add complexity and make this code more and more C-like. So adding more and more features of C into your Cython code so that the code looks less and less like Python and looks more and more like C. And the more of these things you do, the more benefits you can gain from the speed up. Okay, moving slightly forward here, I'll try to keep going here. So let's look at another example of Cython compilation. In this case, we're calculating the Fibonacci series. So the Fibonacci series is a series of numbers such that the nth item in the series is the sum of the item just before it and the item before that. So Fn equals to Fn minus 1 plus Fn minus 2. And here is a fairly naive implementation of the Fibonacci series. Let's say that we want the 10th item or the nth item of the Fibonacci series. We start by pre-allocating A and B to be equal to 1 and 1. And then we loop over the range of numbers from 0 to n, each time replacing A by A plus B and B by A. So this is now the answer that we wanted. When we come out of this loop, we can return A because that's the answer that we wanted. It gives us the answer that we ultimately want. So this is defining Fibonacci series in Python. And here we're defining the Fibonacci series in Cython. Here, we're going to tell it that the input is an integer. So again, this is, in this case, the input is always an integer because we want the item number X or Y. This is never going to be a floating point number. And we're going to define in here that I, A, and B are always integers as well. Notice that I'm using the cdef keyword, and that tells Cython that these numbers are going to be used as local variables within the function, so they don't require much Python operations around them. So we're running this, again, the code. So the code itself, the numerical code itself looks very, very similar, but we've done a few things here. We've told Cython that the input is always going to be an integer, and we've told Cython that these things are always going to be integers, I, A, and B, and also we've cdef'd them to be sort of local variables used within the function. Okay, comparing the two using timeit. So we're running Fibonacci up to the 10th element. And now, as you can see here, the answer is just below here. We get in the realm of a 10x speedup, a slightly more than 10x speedup in this context. So this is already really beneficial. If you have some code and it looks like this, hard to vectorize and contains some nested loops and some simple numerical operations on numbers, you can benefit a lot from using Cython. So here I'll just pause for a second to consider the implications of this. Let's look for a second at the C code required to perform the same calculation as we had here. So this is C code here. If you've never written C code before, it looks not that different from Python. In this case, it looks very similar to the Python. And in and of itself, that doesn't look too terrible at all. It's got some, some more curly braces, perhaps, too many semicolons, in my opinion. But overall, the code is not terrible. It's pretty readable, actually. It's pretty easy to read what the C code is doing. But this is not always going to be the case. Sometimes your C code is just going to be terrible to write. And also, notice that you didn't have to do a lot of the other operations that you need to do when you write C. If you've ever written C, you know that you need to compile it, you need to link it, you need to do all kinds of things. And furthermore, you can use the code, your C code here, within Python. That's part of the beauty here. You can call your C code from within Python. And that's really great because we want to spend time writing Python code, and linking Python code to C code requires writing C extension code, and that's really hard to do. That's a lot more work than what we did here. One of the beautiful things that Cython does behind the hood here for us is to write the C extension code that links, that allows us to import C code into our Python code. So you get the tenfold speed up of the C code without having to write all the C boilerplate and compile it and do all that. So that's pretty useful. There's a little bit of an exercise here about speeding up recursion, but I think that we'll skip over that because this is going a little bit slower than I had anticipated. And also, I just have more material in these notebooks than I really have time to teach. I just mentioned that if you look at the Cython code here, you'll notice that this is not code that looks, it looks like Python, but it's not syntactical Python. If I were to remove this here, then I would get an invalid syntax. This is not code that we could run in Python. There is, however, a mode that you could write. You could write Cython code that works in Python. So this writes the same code that I wrote before for the Fibonacci, but it's all written in Cython library code. So here we're importing the Cython library. We're using some fancy syntax in order to tell us that n is always going to be an integer. We're declaring the variables through a call to a function in Cython, and then we're running the rest of the code here. So this code is equivalent to this code, but it also happens to be syntactically valid Python. So if we remove, we can run this, first we can run this in Cython, and this runs fast, it's 48 nanoseconds. Or we can remove this decorator, this magic, and run this in Python, and then it'll be a lot slower. And so this is sometimes useful if you have situations where you don't know whether you'll be able to compile or not. So here you see it's 1.4 microseconds, actually a lot slower than the compiled code was. So that's sometimes useful. Let me see, there's probably a lot of new questions here. Let's see what questions people have at this point. So Rogers asks, do these optimization approaches blend well with deep learning packages and GPU processing? Well, yes, in a sense, in the sense that you can write a lot of C code that interacts with the GPU, and you could probably get a lot of speed up from that. It's hard to do. It's a lot harder to do. And in fact, if you're going to use the GPU, your path might go better through things like PyCUDA rather than through Cython. Combining PyCUDA and Cython, I'm not even sure if that's possible. Maybe somebody else here knows and can write more about that in Slack. I've definitely never tried doing that. It could be something to try. It would probably make things, if you did that well, it would probably make things run blazingly fast. Okay, more questions here. Is there a disadvantage to using Cython for your functions except verbosity? Well, you need a C compiler present. That's a real disadvantage. So notice I kind of glossed over this a little bit, but I told you that when I run this code, what happens behind the hood is that Cython takes the code, it compiles it into C code, and then it uses a C compiler to compile that C code into machine code. So you have to have a compiler installed here. If you don't have a compiler, this won't work. Also, you have to compile the code separately for every platform on which this will run. So this works well if you're working like us on this machine that you have provisions through a Jupyter Hub. But if you're writing some code that someone who works on a different platform from you works on, for example, you're writing your code on Linux and you want to give this to a friend who works on Windows, that's going to be really hard. You're going to have to find a Windows machine to compile this for Windows and compile it for every, for different configurations, for different platforms. So that makes it a little bit more cumbersome. So that's definitely a disadvantage. Does Cython mostly improve numerical operations? Could it also speed up operations on strings like regexes or web scraping? I actually don't know the answer to that question. I've mostly seen it in numerical code. I have no idea, but maybe somebody else here knows that and could point to some nice Cython acceleration, maybe in the Slack, of non-numerical, regex, web scraping, and so on. That's a really interesting question, actually. So I'm just checking. Mark this answers. Can any of these be translated to cloud computing platform like AWS? Absolutely, yes. If you can compile your code for the platform you're running on, AWS runs many different operating systems, including Linux, and you can run it there. And we'll talk more about cloud later this week, and I can kind of show you how that works if you want. Is there an issue embedding non-Cython functions into other Cython functions? So no, one of the beautiful things about Cython is that I could write Python code here. I could write standard Python code in here, and it would just get embedded into my Cython code. In fact, one way to start writing Cython is to write the function that you want to write in Python and compile it, and then start annotating the things that you think you can annotate with things like type definitions and with other kinds of annotations that Cython provides, and then go from there. So one way to increase, and then keep measuring, every time keep measuring using a profiling tool like TimeIt. How much improvement did I gain from adding this additional annotation, this additional optimization? That's sort of a standard way of working with Cython. All right, cool. I think that I'll move on ahead. Hopefully I haven't lost too many of you. Okay, so I'm gonna show you one other mode. I think this might interest you if you're thinking about, now you've seen this demo operating in the Jupyter notebook, and you might be thinking, well, how do I combine this code into some library code that I'm writing? And tomorrow we'll talk a little bit about library code as well, and how to build shareable libraries, and I'll go step by step over this. For now, I'll show you just a little tidbit about how you might create Cython code that you can embed in a library. So, and this will maybe give you a little bit more of an intuition about how Cython does what it does under the hood as well. So this will show you a little bit of the mechanics as well. So here we're gonna break out of the notebook. Actually, this is all written into the notebook, but I'm going to show you how this works not in a notebook. So I'm going to, in this folder, I'm going to start a Python file. I'll rename it to, oh, sorry, this is going to be a Cython file. I'm going to move this, and I need to rename it. And I'm going to rename this fib.pyx. So pyx is the extension for Cython code. It's very similar to py, but it's not exactly Python. And I'm going to copy the code that we wrote before here into my pyx file right there. So I've written the pyx, the Fibonacci function into a pyx function, into a pyx file. Now I'm going to create one more text file here. And this text file is going to be renamed setup fib.py. So this is going to be my setup file. So I have two files here. One is, can I open this? What did I do? Did I create the wrong kind of file? Maybe I created the wrong kind of file. Text file. Setup fib.py, not txt, like that. Oops. Dismiss. Oh, this is a notebook. I don't want this notebook, so I'm going to delete it. And then I'm going to rename my text file here into setup fib.py. Alrighty. So I have this setup file here, and I'm going to copy some code here, and I'll explain this code line by line. It's in the notebook, but I'm going to copy it into the setup fib.py. So this code here is the code that tells Cython where to find the extension code and how to compile it. It uses several different things. Distutils is one of the Python standard library packages that provides tools for distribution of code, for compiling extensions, for packaging libraries, and so on. I'm also importing from Cython.distutils a function called buildExt that tells the Python code how to build the extension. And so I'm generating an extension, a distutils extension. I'm telling it I'm going to call this extension fib, and the source for this extension is going to be my fib.pyx Cython file. And then I run a function called setup. This one takes as optional inputs what are my extension modules, and as an optional input, what build function should I use in order to build this extension. This is a little bit complicated, but stay with me here. The next step that I will do is that I will run this setup function in the terminal. So I am, sorry, still in the same folder here. Oops. Performance. Okay. So here I'm going to get a terminal window right here. And I am in my terminal. So this terminal window can also be used. So this operates like a standard Unix shell. And I can go into curriculum and into Monday, hi, and I'm tab completing here to get me into this. And I can see that I have here my setup fib.py and my fib.pyx. And I'm going to run the following code: Python setup fib.py build ext -- in place. What this does is it tells setup.fib.py to run the build extension command and then to leave the extension in place in where we're doing this. So I run that, and what you'll see that Cython has done in the background now is that it's gone and it's compiled. So first it's Cythonized my fib.pyx into fib.c. It wrote a C code file out of my Fibonacci code. And then it complained about something, and then it built the fib extension, and then it ran GCC, which is the C compiler installed on this machine, to create an object file. And then it ran another thing, I believe, in order to link this up so that now Python can use this. So this is good. You'll see that several new things have been generated inside of my directory here. First of all, there's this fib.c file. Let's look at that. This is the C code that Cython wrote when I asked it to compile my code. So here's some C code. And you'll see there's a lot of stuff going on in this code. There's a lot of boilerplate at the top here. And then there's some more boilerplate. And there's some Python extension code here. And then there's some more code and some more code and some more code. And this is all C code. And this is all the code that we need in order to run the C code. And there's lots of different cases here, lots of different things you can do with this code. And it's about 2,700 lines of C code written out of that little snippet of Fibonacci code that I wrote in Cython. So what you can see is we've sort of, if we would want to write by hand the C code to do all this, that would be a lot of work. So it's great that we can automate it by writing this C code through Cython. But the next thing that we'll see is that now that we've compiled and created this, in this build directory, we have some fib.o, which is kind of object code that we can directly import. We can now run import fib here. Let me run import fib first. And that imports it imports the extension code into this notebook such that I can now run let's see, and a is equal to 144. So fib is now treated as like a library or a module that I can import into this namespace, into the notebook, and then run the fib function inside of the fib library that runs the Fibonacci series in the same way that I ran before. So this is all pretty neat. Okay. Right, so Faisal here points out in his question that there's some guides in the documentation about how to do this thing. I kind of walked you through that here, but you can read a lot more about this in the Cython documentation. I'd recommend doing that. I'm here really just scratching the surface. Cython is a very sophisticated library. We're scratching the surface here, and we've probably reached just about as much as I know about Cython. Let's see what other questions you have at this point. Oh, okay, yeah. So this all, I think, is now answered. Okay, what other questions do you have about Cython? If you haven't been following me with this last notebook, just bear with me. Things will become a bit more comprehensible in just a moment as I shift gears to show you the next clever speed up opportunity. How do we learn more about Cython apart from the documentation, which may or may not be well kept? What do you recommend? So I recommend actually a series of really great blog posts from Jake van der Plas. Jake van der Plas used to be my colleague at the University of Washington until about a year ago when he moved to work for Google, working on their open source software. And Jake van der Plas wrote a few years ago a series of blog posts that I will dig up and link to in Slack that really explained very well how to use Cython and how to use it cleverly. So I think that's a really great starting point. Okay. So I'm gonna cut short things here for the sake of all of our sanity and time. And I will next go to talk about a different approach. So there's a lot more here, and you can read more about these notebooks about other things that you can do. And like I said, you can learn a lot more about Cython looking at those blog posts from Jake and from many other resources, documentation and other things. I'll link to other resources as well. There are some great online tutorials and videos from past SciPy conferences and so on. What I'll go to next is instead go straight to Numba, because I would like to get eventually to Dask, because I really like Dask, and I will want to show that to you. And there's only so much time we have together today. So let me just tell you quickly about Numba, because I think it's really clever and it's very simple. And it does a very similar thing to what Cython does. It takes your code and it compiles it into highly optimized machine code so that it runs faster. And so the approach here is slightly different. In contrast to writing out this C code that I showed you and compiling that code through the compiler, Numba instead uses a technology called LLVM that does what's called just-in-time compilation. Just-in-time compilation means that the compiler looks at the code as it is running and observes what it does, and then does some clever things behind the hood to write optimized machine code out of that. Let's look at how that works. So the library that does just-in-time compilation is called Numba. You can install it on your machine using Conda, but we have it installed on the Jupyter Hub for you. And let's look again at this Fibonacci example that we used before. What we're going to do is we're going to import from Numba a function called JIT. JIT stands for just-in-time compilation, or just-in-time. And we're going to create a new function called fibj that is the output of JIT on fib. So we call a function called JIT on the fib function, and we get as output another function called fibj. Okay. Having done that, we can time the execution in both of these. And we're getting fibj, 750 nanoseconds. And right, and we have to run this more than once to see the speed. So first time that we ran it, they're pretty much the same. And that's because the first time that we run this code, the compiler looks at the code, and under the hood, it does some clever stuff in order to compile the code. So first time we ran it, it took 715 nanoseconds, and that's about the same time that it took to run the fib function. But next time that we run it, we get a roughly threefold speed up in execution, a slightly more than threefold speed up in execution, just by running this code over our function. So that's kind of magical. We don't need to do a lot, and we can get threefold speed up of this kind of code. I'm pointing out this kind of code because really Numba will only work well in very particular kinds of cases. Before I talk a little bit more about when this works and then where this doesn't work, let me just point out that you can use this JIT function as a so-called decorator. Decorators in Python are these clever constructs that allow you to take a function as input and produce a function as output. And so if you have a function like JIT, this JIT function that we got from Numba, and it operates in this way, it takes a function as input and provides a function as output, you can often use it as a decorator. So this is the decorator syntax, if you've never seen the decorator syntax before in Python. At JIT precedes the function definition for our fib function. In this case, we call it fibj because it's decorated by JIT. And that means that this code will get defined, it'll get run through JIT, and then it'll be returned to us with the name fibj. So this piece of code here does the same thing that this piece of code here did. It takes the fib function and compiles it using Numba, or prepares it for JIT compilation using Numba, and then gives it back to us. So this is equivalent. It's just, it's sometimes nicer to use this decorator. And you might see code of this sort when you look into more advanced use cases of Numba, you might see code of this sort. So I thought that I would point that out here. Okay, let's talk a little bit about how Numba works and when doesn't it work. Numba works really, really well when it can figure out, when the data types that you use here are kind of a very standard Python data types, and when it can figure out how to make use of the structure of your code, how to unroll this loop, do various tricks under the hood in order to make this loop go faster. But if we create something a lot less transparent, Numba will fail pretty badly. For example, let's think about a case where we have a fancy Python object, a Python class that represents integers. So this is the class myInt. It's derived from object. It has an initializer, and in this initializer, we store an attribute called self.int. We store the number that was given in input as an integer. So this is a class that wraps the Python integer. It doesn't do anything very clever, but it does wrap around, and it has all the machinery of Python objects. So it's really not as transparent as a Python integer. So let's see, let's define this other code. This code is the same as the Fibonacci code, except now I'm using the class, right? You give me the number n, I'm going to initialize a and b with myInt with 1, myInt of 1, and then for I in range n.int, I assume that n is also a class instance of the class myInt. I'm going to use the integer in there to loop over and over, and in every iteration through, I'm going to access the attribute int in every one of these variables, and I'm going to redefine the int attribute in these objects. So I'm doing access into these objects. This is not particularly useful code, but it does demonstrate the fact that sometimes you have fancy Python objects that you would like to use. Imagine that this code was using, I don't know, some nice scikit-learn objects or something else that has a lot of object orientation. And now let's take this and compile a JIT compiled version of this. We call it fibobj_j. So what we'll find, let me add another cell here. So I'm doing Control and A to add another cell here to do time it of fibobj my int 10, and you'll see how that works. So that takes 3 microseconds to operate. So it's pretty slow code, and that's because it's got all this object orientation in there. Let's see what happens if I try to run the numba JIT compiled version of this code. First of all, it warns me of a lot of things. It says this compilation is not going to work for you. This stuff doesn't make sense. We can't determine what to do with this myint. And then also it takes 168 microseconds to run compared to these 3 microseconds. So this is hundreds of times slower than the original Python code. And it throws a lot of warnings. It's actually pretty useful that it throws all these warnings. It tells you, look, what you did does not make sense. So don't do this. And so this kind of code that requires a lot of interaction with Python, fancy Python classes that are not transparent to numba, just won't work that well. So this is an example of a case where things just don't work that well. And it's really, the cases in which numba really shines are cases where you can write code that looks a lot like the code for the distance function that we saw at the very top, right? This code has nested loops in it. It has several nested loops in it. It's really slow in Python, but this would go blazingly fast in numba. This would actually be sped orders of magnitude if run in numba. I won't demonstrate through this code, but this notebook that I'm not going to go over all of it because I want to still go over the code for Dask, which is the next notebook. So I won't go over all this numba example, but this code here demonstrates a little bit more in detail a comparison between NumPy, numba, and Cython. And really, numba, this is where it shines, where the code is the kind of code that you would have to write if you wrote math that includes several nested sums, several nested integrals, a lot of physics code, a lot of code that implements recurrence, for example, might look like that. It's very hard to vectorize, can be written like this in a way that resembles the math that you're trying to write very closely, but really is very slow in Python, can be sped up substantially using numba. I was asked before about the combination of Cython and the GPU. And I won't show here, but I will mention, and this should be maybe in future versions of this lesson, that numba is written with a lot of ways to optimize code using the GPU. Numba really does take into account the GPU. There's a lot of functions in numba to load data into the GPU, operate very quickly, very fast on data that's stored in the GPU. There are ways to really use the fact that the GPU is there to optimize code that, for example, does image processing operations. If you're interested in this kind of thing, I'd recommend looking into Stencil Computations in numba. The name is Stencil Computations. So you define a stencil and you run it over your image, and it can run very fast. And if you have a GPU on board and the image is already loaded into the GPU, you'll get orders of magnitude of speed up. Okay, what questions do people have at this point? Can you store a compiled version of the optimized numba function after running it several times? That's a really good question, and is a relatively new feature of numba that, yes, you can actually store on disk kind of like a compiled version of the numba. It used to be that you had to run it once in order to get the compilation, but they implemented in more recent versions of numba, they implemented the possibility to cache, to store the number compiled code. The other question here is, when would you use Cython and when would you use number? And that's a really good question, and one that's hard to answer. I think my order of operation would be to see whether number speeds it up substantially. If I can take my code and really literally, I hate saying the word just when I talk about writing some code, but if I just do this, right, I just run it through some JIT compilation and I get speed up, then that's great. If I haven't gotten that, then I need to make some more effort. And maybe if this is a true bottleneck in my code, then I have to go to Cython and try starting to type annotate and do more. I will say you can also do some type annotations in Numba. There's some systems for type annotation there. So it's kind of a hard question. It's a lot of this requires some empirical sort of trial and error, I'd say. Okay. Would Numba or Cython be able to interpret data type when a third-party engine is supported, like Matlab? Oh, wow, that's a hard question. My guess is that no. Combining this with Matlab would be just really hard. And I speak from experience because I once wrote a Python MATLAB translator, or sort of like a library that allowed you to pass back and forth data between Python and MATLAB, and it was unpleasant. So I think this would be really hard. Okay, is it bad form to have some parts of your code in normal Python, some that use Cython and some that use Numba? No, not bad form at all. You might have, if you're writing library code that does a lot of different things, and some of it is better optimized in Cython and some of it is better optimized in Numba, then go for it. I actually have an example of that. Code that I wrote with a postdoc that worked with me, and actually now is a professor at UCSB. I'll mention his name because he wrote a lot of Numba code, he wrote a lot of Cython code. His name is Michael Baylor, and in his postdoc and now in his own lab, he writes code for simulations of retinal prosthetics, and these simulations operate on large grids of images, and some of that code is optimized using Numba, and some of it is optimized using Cython. So we mix and match as we can. You're definitely allowed, that's a hard question, in pretty much any context. Okay, you may have mentioned this, but it sounds like Numba would not work well with scikit-learn. It's going to be really tricky. It's going to be really tricky to use complicated Python objects like the ones that are implemented in scikit-learn and really just get out of the box improvement on their performance with Numba, is my opinion. But worth trying. I haven't really tried that. But my intuition, based on what I showed you before, is that's not gonna do very well. Okay. What other questions do people have at this point? I'm just going to do a quick sanity check for myself here to just give you a little breather to make sure that I understand correctly the timing of the next presentation. Okay, yeah, so my goal is to have a little break before the next session, and we're headed in that direction. And so I will, oops, you don't really need to see my calendar, do you? Okay, so I'll head into Dask and I'll spend some time with Dask because I really like Dask, and then we'll take a break before Fernando's presentation. Okay. Let's go into, so if no other questions, I see no other questions here, but maybe I should check on Slack if there's any other things. I see that there's some conversations here, but I think we'll also catch up with Slack later after this presentation. You can go there and have continued discussions on these topics. Okay, so next to Dask. Dask is the next topic. So the things that I showed you until now are ways to improve the performance of Python by using compilers, whether it be, the good old C compiler to write C code and then compile the C code and make it go really fast. Excuse me. Or to use this slightly newer tool chain called LLVM to do just-in-time compilation. Since I mentioned Jake Vanderplas, I should mention that Jake Vanderplas is now working on another just-in-time compilation system that Google has called JAX, J-A-X. And I haven't experimented with it much, but it uses a slightly different approach than Numba for just-in-time compilation. And it's worth checking out as well if you're thinking about combining, using a GPU to really accelerate your code. If you're doing a lot with the GPU anyway, JAX is really worthwhile checking out because that's the target, I believe, of JAX development, is to work really fast, do just-in-time compilation, 4 operations on the GPU. So I'll just mention that here, but I won't show any JAX code. And you can check out, Jake just gave a talk at the SciPy conference, and I'll post that link as well later on. Jake just gave a talk about JAX in the recent SciPy conference, and Jake is a great speaker, so it's a great talk, and JAX looks really promising. So that's compilation. Let's talk about parallelization now. So again, as I mentioned before, out of the box, when you use Python, it will run on a single thread, and that's because what's called the global interpreter lock. The idea is that the interpreter can only deal with one thing at a time. So if it's busy doing one thing, it can't be doing anything else at the same time. And though there is, in the standard library, there is a multiprocessing module that basically spawns off different processes or different threads and runs the code in parallel. Writing code in the multiprocessing module is really cumbersome. It's really hard to write code for the multiprocessing, and it's very hard to take advantage of that, especially in the context where you're doing scientific development, you're working with NumPy, data types, and so on. The standard library just doesn't know about these things as well. And so the beauty of Dask is that it gives you access to these kind of multiprocessing capabilities and multi-threading capabilities that exist in Python, but also is cognizant of scientific computing use cases. So that's really clever. We'll see how that works and what it can do for us in the neuroimaging context. Let's start with a really simple example taken from the Dask tutorials. Here is some code. I'm going to import the standard library timing library, time. I'm going to define a function called increment, or inc. It takes as an input a variable, and it adds the number 1 to that variable. So the input is x, the output is x plus 1. But inside that code, I'm going to insert time.sleep1. And the reason I'm introducing that is because this takes almost no time at all, and I want to simulate some code that does some complicated numerical operations. So my sleeping here simulates, oh, there's a lot of code here and does a lot of operations, and that takes a lot of time. It takes a second to run here in between. Okay, in addition to this code called increment, or inc, I'm going to define another function called add. Add takes 2 inputs, x and y, and it adds them together, returns x plus y. Again, to simulate some work, I'm going to add a sleep in there. So it sleeps for a second and then gives me the output. Okay. So now let's look at this series of operations. How long would it take to perform these operations? Well, instead of asking you, because you're not right in front of me, I'll go over the considerations. You go here, you give it the increment, the 1, goes in, it sleeps for a second, and then returns to you 1 plus 1. Good. It goes here, sleeps for a second, and then returns 2 plus 1. And then it goes in here, sleeps for an entire second, and then returns you the addition. So taken together, 1, 2, 3 seconds. That would take about 3 seconds to run. And indeed, when I execute that, we're waiting here, and eventually it comes back. Okay, but there's something to notice about this code. And that's noticing the data dependencies that exist in this code. And that's the fact that while z, the output, the result, the final result of this computation, depends on both x1 and x2, x1 and x2 themselves don't depend on each other. If we had access to parallelization, we could compute x1 in parallel to the computation of x2. They have no dependency between them. And that's exactly the kind of functionality that Dasks afford to us. So here's what Dask does. Dask has a function in it called delayed. And what delayed does is that it takes a function and returns a function to you. And that function is now delayed. So we're going to delay the increment function. And we're going to take that delayed function, delayed inc, and run it over, run it with the input 1. And then we're going to delay increment again. We're going to take this delayed function and run it over the input 2. And then we're going to delay the add function and run this delayed function over x1 and x2. And when we do that, it goes really, really fast. And that's because no computation has happened yet. Let's add another cell here and look at what Z is. What Z is it's stored as this object called a delayed object that has no value yet. We've delayed all these computations so far and haven't executed any of them. In fact, the computation itself only takes place when we run z.compute. Okay, run z.compute, and I'll ask you how much time did this take? And I'll answer this question also. This took 2 seconds to run. And the reason that that took 2 seconds to run becomes apparent when we visualize z. So this delayed object that we have here has a visualize method. And when we call it, we see this graph of the execution. So what Dask is doing under the hood, we call this delayed function and decorated this. What Dask knows to do is knows to look at the dependencies between all the functions that are written into this code. So when it looks and it sees, it says, well, the final result up here of the addition depends on 2 variables. It depends on the output of increment on the one side and the output of increment on the other side. But these 2 don't depend on each other, and those can be executed in parallel. So what this little snippet of code did for us is it parallelized the execution of these 2 increment operations. It did those 2 in parallel. And it did those 2 in parallel only when we called z.compute. The reason that we have to defer the computation until after we've written all of this code is that before we write all of this code, Dask doesn't know how to put together this computational graph. It has to have all the information. It has to know that we're going to input here x1 and we're going to input here x2, and those came from delayed executions of this other function. It's only after that it's seen all of its code that it knows that it has all this code put together in this way, and that can construct this graph. And only when it has all of that can it actually execute the computation, the parallel computation, only after it can reason about the task execution graph. Okay. What questions do people have at this point about what Dask does? Would Dask work with functions that operate each on different rows of the same matrix? That is where we're headed here. So once we do this with, so this is the question that Rogers asked here is, well, we could parallelize. Let's say that we have a big matrix and we're doing the same operation on each row in the matrix, and operations in different rows don't depend on each other. Could we parallelize across the entire matrix, across each row of the matrix? And the answer is yes, that's exactly right. If Dask knew about, for example, about the structure of NumPy arrays internally, it could do that very well, and it could do it very fast. In fact, that's where we're headed here. We'll get to that in just a few rows. Do you need delayed around Z at all for it to work? No, notice that there's no delayed around Z. There's a delayed around add. So we need to defer the computation of the addition. I believe if we didn't have this delayed around add, I don't think this would work well. Oh no, I might be wrong. It might be possible that if it gets delayed, so it might be that you don't even need the delay of the add. Once it gets delayed objects, it knows that it has delay its execution as well. Yes. Good point. I didn't know that, but that's really clever. Yeah, if the add function gets 2 Dask objects, somehow it infers that that needs to be delayed as well. So that's neat. It makes the code a little simpler. Thank you. That was a great point. What other questions do people have at this point? All right. So I'm gonna move on to try to answer the question that Roger's asked about doing this with slightly more sophisticated data types. Especially, let's think about a lot of our work is done with large arrays of data time series or images and so on. So let's look at some fMRI data. Oh, that's interesting. Oh, I know why this is not working. There you go. So I've downloaded some data into the data folder. You each have a data folder, by the way. I didn't mention that this morning, but maybe I should have. There's a data folder here that contains lots of data. This data folder is read-only to you, and it's write and read for the instructors. So we put lots of data that we're using in the various tutorials in there. And I've downloaded some data from the OpenNeuro DS000114 here inside of this folder. I've downloaded some MRI time series from some tasks, different tasks that were done in this experiment. I'm not even sure what this experiment was. There was some test and retest data. I think maybe it was something for test-retest reliability. At any rate, some data. And I'm going to try to read all this data in memory and do something with this data. So here I am using the glob library in order to extract the file names. So here I have a series of file names of these file names that I just showed you. Okay. I like to use NumPy in order to do array operations, and I'd like to use NeBabel in order to read the data from file. You'll hear a lot more about NeBabel in a couple of days from Chris, but for now, suffice to say that when I do nib.load with a file name, and I get the data, the floating point data from there, what it does is it opens the file, it reads the data into an array, and here in this case, it appends it into a list of arrays. So that when I run this code, concatenating all this data into one big block of data made out of all the data in all these files concatenated together along the last dimension, the time dimension, and I take the average along the time dimension and divide by the standard deviation on the time dimension, I get the temporal SNR. I didn't run this code, so that didn't work, but here I'm running this. It computes the temporal SNR in every voxel. The mean in that voxel divided by standard deviation across all these scans. And that takes a little bit of time to run. Let me just see. The question that still exists here is, so compute is actually doing the parallelization. Compute is actually executing the graph. The call to compute is what executes this graph and gives us this result. It materializes this result. I hope that answered that question. Okay, back to this case. So we'd like to do this. Noticing this, we notice that the concatenation does depend on having all the data in memory, but the loading of the files from disk actually doesn't depend. The loading of each array doesn't depend on others. So can we maybe parallelize the loading of data from disk so that we can do this faster? And the answer is yes. And we're going to use a little bit of a feature of NeBabel, and that's the fact that when we call the load function in NeBabel to load a nifty file from disk, it doesn't actually execute the call. It doesn't read the data from disk. What it does here is it loads some metadata about the file, and it prepares to get the data. But the data doesn't actually get read from disk. The expensive operation here of reading the data from disk doesn't get executed until we call this getFdata function that does the heavy lifting here. So what we can do here is we can say, for this object, this nifty image object that we have that reads the data from file, get the method of that object, getFdata, and delay it. Delay it with dask. Delay that call so that now what I can do is I can go file name by file name, and I can append into a list a delayed call to the getFdata function on the loading of the file. So this is equivalent to the call right here, but it's delaying the execution of this call to the method. So we're not going to execute that until we really need it. and I'm going to delay the concatenation of the data, and I'm going to delay the call to the mean. I'm going to delay the call to the standard deviation down here. Now, based on what we discovered before about maybe not having to delay this, maybe we don't need to call all of these delays. Well, let's just do this for now. Let's visualize the TSNR in this case. And this is what we see in the TSNR case. It says, well, I can get all these files separately. But then once I want to concatenate them, that's a bottleneck. I have to do all the concatenation together. And then I call the mean and the standard deviation. These two actually don't depend on each other, right? Calling the mean here and calling the standard deviation don't depend on each other. So I'm going to do those in parallel. And then I'm going to use a division, the division function here. I have to divide them one by each other and give you back the result here at the top. So this is the visualization of this thing. And that should work faster for me. I haven't computed this here, but let me add a cell down here and then do tsnr.compute. And I haven't timed this for you, but you'll have to trust me that it goes faster. And you might have felt that even though it went a little faster than our previous attempt at doing that. And it gives us back an array. There are a lot of nans in here because there are a lot of zeros, but that's sort of the detail of the computation. Let's see what questions people have. So quite a lot of neuroimaging commands incorporates parallelization. So if we have to use Dask on top of that, does it auto-optimize available cores, or is it something we need to take into account? Right, so the question is, there are a lot of code that's already written with parallelization, right? If you call FSL or something else, it might already have parallelization implemented. And maybe in that case, you don't need Dask. But I'm going to encourage you to write some NumPy code that does things that maybe FSL doesn't do for you, right? In some cases, when you're hacking, you want to do something that no library. I mean, I definitely endorse things that Russ said, that if you want to do something and there's a library that already does it, use the library that does that and does it well, and it's developed by a community using best practices. But if it's not, if you're doing something novel that nobody else has done and you're writing it using NumPy, then using Dask, like we did here, makes sense. And can give you substantial, in this case, it gives you substantial speed up, just because in this case, the most expensive operation in the whole shebang here is reading the data from disk in this case. And it's fairly easy to decorate your getF data with the delayed and then delay execution of that until you actually need to do that. And Dask has a lot of information to reason about how to delay things. Okay, let's read this down. Could you add the delay to add nib.load? And Chris has already answered. That's a good question. We could have tried to delay the loading, but as Chris mentions in the answer here, the call to load is really cheap, and that's because it just reads some header information for us. And we're going to use that in a little bit to do something even more clever using that header information. Some of that header information is actually useful to us when we do this, and that's because if we give Dask a little bit more information about the data, it can do even better. So I'm going to mark this as answered, and yeah, so this, nib.load.getF data. Okay, the question was really more about this line here. So the tricky thing here is to notice that nib.load returns an object of type nifty1 image. And so the call to get F data here is executed on an object of type nifty1 image. It's not that the load itself had to get F data method. It's the object returned by this call to F name that has the get F data. And this is the kind of object that gets returned. So we do this instead of doing, as in the question that Matthew asked, delaying the nib.load.getF data. This is a good question because it's kind of confusing the way that's written here. Okay. And then finally, Virgil question here: can you use decorator syntax for delayed? Yes, you can. Good noticing and remembering the decorator. Notice that delayed is a function that takes a function as input and a function as output. So we could decorate instead. We could have written something like add delayed def inc, and then written the function here, and so on. And that would have given us a delayed function. So maybe we call it delayed inc if we want to be sure, right? So this gives us the delayed version of that function. As I said in the previous example, is it true that we would not need the delayed around the TSNR since we have it around the data function? I leave that as an exercise to the reader, as they say. Let's experiment with that later, and let me move on to show you just a little bit more here before we the notebook. You have the notebook, so you should try experimenting with that. I'd be interested to hear how much of these call to delays we can actually remove. Okay, so let me just do one more little thing here before we take a little break for the afternoon and then reconvene in about half an hour for Fernando. So this will take another 10 minutes or so, and then we'll stop here and take about 20 minutes for a break. Okay, so let's talk about Dask arrays. So, okay, we've done very nicely just by reasoning about data dependencies on arbitrary objects. Dask notices the dependencies and computes something. But what if Dask knew a little bit more about our objects? One of the ways that Dask is just phenomenal and clever is that it implements APIs of popular libraries as Dask operations. So I'll tell you about two things that Dask does, and then I'll demonstrate one of them. The first is that there is a Dask data frame object. The Dask data frame mimics the operations of the pandas data frame, but does it in parallelized chunks. So think about the example that Rogers was asking about before. Let's say that there's some operation that we wanted to row by row on a big table that's stored in a pandas data frame. If you're not familiar with data frames, it's not too important. What Dask will do is it'll chunk that data frame into chunks automatically behind the scenes. It'll chunk your data frame into chunks and then do as much parallelization as it can on this, either row by row or maybe chunk by chunk. And often it's better to do chunk by chunk because there's some overhead associated with the parallelization. So that's neat. Another example of that is the Dask array. So if you're using NumPy arrays, Dask array implements an API, an application programming interface or an interface that resembles the NumPy API very closely. So here's how that works. There's a submodule or a library within Dask called Dask array. We import it here as Dask array. And then we're going to create an array from a delayed object. So here we go. I've broken this up into two lines of code. In the first line, I call nib.load. Remember, nib.load just reads a little bit of metadata for us and gives us back this object that needs getData called on it. We call the delayed version of getData on it. And then we create from delayed Dask array from a delayed object. Dask array can come from various sources. It can come from an array that is in memory, or it can come from a delayed object. In this case, it comes from a delayed object. You can create a Dask array also from an array that's in memory, and parallelization would work in the same way. Here we're creating it from a delayed object. And the neat thing about this is that we can tell Dask array about the shape, or rather we have to tell Dask array about the shape of the object. The shape is stored in the header. So we don't need to read the data in order to get the shape. We can get image.shape from the header information, and we can get the data type. So we need to tell Dask about the shape of the object we're going to read and about the data type at the very least. And so when we call this code, we get a list of these delayed arrays. Notice that Dask now knows we have these Dask array objects, and Dask knows things like what is the shape of this object, right? This one has 184 time points, this has 76, and so on. They all have the same first three dimensions, which are the spatial dimensions, but the length of the time series is different. And it tells us about chunk sizes. You can chunk this into different levels of chunks. Remember, I told you can either take one row at a time or many rows, and you can control that. That's the chunk size. In this case, it's determined that the best thing to do is to just leave these chunks as they are. And each one of these is a NumPy array. And then we call the Dask array concatenate function. This is just like the NumPy concatenate function. Rather, it is a version of the concatenate function that operates on a list of delayed arrays. So when we run that, we get a delayed array that contains all this concatenation. Maybe we can look at what that looks like. So array is, and this has a nice representation in the notebook. It tells us, oh, hey, look, I got an array. It's got the following shape, 759 time points on the last dimension. And it's got 5 chunks. You can even see the chunks delineated here. The chunks are of different size because each file has a different number. But it hasn't read the data yet. It just knows about this data because we told it about it. And then we calculate the TSNR, calling the mean method on this array, and the standard deviation method on this array. And then TSNR is, again, a delayed Dask array. Notice that the last dimension here was reduced. That's because these operations are reductions of the last dimension. So we end up with a TSNR map that is 64 by 64 by 30, which is the spatial dimensions of these scans. Cool, let's visualize that. So the nice thing about this is that given all this information about the arrays, Dask can optimize even more than it could optimize before. Let's go to the bottom of this. So the first thing that it can optimize here is the calls to get F data. It does the same way that it did it before, calling these get F data in parallel. But also it notices that because these are arrays, there's a more clever way to compute the mean and the variance. And that's because the mean of a big concatenator array is the weighted mean of different parts of that concatenator array. So we can calculate the mean of every chunk and then combine that mean here, okay? And we can do the same for the variance. There's a similar idea that you can compute the variance as well from a series of variances. So each variance can be computed in parallel as well. And then you combine these variances, you aggregate them together. You take the square root here because the standard deviation is the square root of the variance. So you don't want to take separately square root every time. Instead, you just defer the square root computation to the top here. And then you divide and you get your answer. So given all this information about the data type and about the shapes of these things, Dask can do a much better job of creating this kind of graph. And these representations of these graphs are terrific for getting an intuition of how much parallelization you're getting out of that. Okay, and then in the end, you can compute this thing, and you'll just have to take my word for it that it gives you a further twofold speed up over, over this parallelized version. So you get some speed up from this, just from the parallel reads, and you get an additional speed up from the knowledge that these are arrays and from this additional information that you provided in this case. Okay, what questions do people have? Are Cython and Dask integratable with one another? Yes, so you can definitely integrate Dask and Cython together, and that would be really great in the sense that if your Cython code takes as input arrays, for example, and you can do all this clever stuff with arrays. I will say the nice thing about this array API is that it has a lot of these methods of the arrays implemented. So if your Cython code is some really complicated operation with the array that gives you no insight into how to split it apart in this way, then you're going to get less from it than you would get from kind of the core things. I will say that Dask, in addition to implementing these kind of basic APIs like the mean and the variance and so on, aggregations on this data, it implements, for example, very complicated linear algebra operations on these arrays. For example, there's a parallelized SVD. If you use SVDs to solve sets of linear equations or to do PCA or something like that, you can do that over very large arrays in parallel, which can give you a lot of speed up. Just as a final sort of teaser, Dask also operates over data that is distributed. So if your data is not even co-localized, but instead distributed over a cluster, you can point to different bits of the cluster and say, I want different parts of the cluster to do different parts of this graph for me. And so, for example, you can do operations on very large data sets. So for example, imagine that all your data would take more memory than we have on this machine, or more memory than you have on any machine. You could still ingest all this data on different machines, do your SVD over this very large array, maybe hundreds of gigabytes of data, terabytes of data even, do an SVD in parallel, combine the information to get, I don't know, singular values out of that, or PCA out of that. So that really can do phenomenal things. They're just not possible to do otherwise. Until now, I've shown you how to speed things up. Now I'm telling you, you could probably do things that are just impossible to do without Dask. Okay, let's see what other questions people have. One more question about parallelization. What are the constraints on how many threads you can process in parallel? I ask because I'm not familiar with how parallel computing is supported and the hardware involved. To be honest, I'm not entirely sure on the hardware side of things either. There is definitely a trade-off. Each thread, each kind of parallelization a fork out of the main fork has some overhead associated with it in memory and time. And so how you chunk your data, let's say that you have a big matrix like this one that has lots of time series, 64 by 30 by 64 little voxels. It's rarely the case that you want to perform this operation separately on every voxel. And that's because getting all these voxels into a queue and getting them off the queue and so on, that in itself costs. So unfortunately, there's no like clean answer here, but figuring out how to chunk your data turns out to be an important thing that you need to do, and depends very much on the particulars of your configuration, how much RAM you have there, how much CPU, and other low-level things that I know too little about. I hope that answered that in partially a satisfactory manner. All right. What other questions do people have at this point? Okay, if no more questions, I'd really enjoy it if you continue to experiment on the hub with these ideas, with these things, and kept the discussion going on the Slack channel. And we can continue to play with this. If somebody's interested in doing some kind of hack with Dask, I'd be really stoked about that. And for now, I'm going to stop. First, stop sharing, and then stop talking. And I'll see you all soon.